All right, so today is the last day before the exam. And so I think what we'll do is we'll just start reviewing. And as I said before, for the exam, bring an exam book. I'll give you all a copy of the scriptures.
That's funny.
And here is the last homework assignment back. So, so we're on the review session. The review session is on for Wednesday at 6. Okay.
It's not pulling a rabbit.
Yeah, I commented on a few people who pulled a rabbit out of a hat. Oh, by the way, there's one thing I want to show you guys before we go on, before we start reviewing. Check this out. I think this is kind of cool. What I've done here on the screen is, you know, the author of the book, Professor Grease, he's at Cornell. He printed up a solutions manual where he did all the solutions to all these problems for instructors, you know, to help grade proofs. And look at this. For his problem 3.33 in the book is to prove De Morgan's law 3.47b. And look at this proof that he has in his solutions manual. I reproduced this from his solutions manual. It starts with not P or Q, and he gets it to not P and not Q. But the way he does it is he goes through with the golden rule, and he uses 3.32 twice. In other words, he does it just the same way that we proved 3.47a, the De Morgan's law A, the first De Morgan's law. So he has this long proof. But then, look what he has also in the book. He says, here is a second proof, which is one step shorter. And so he goes through and says, and does the golden rule, and then he uses De Morgan 3.47a, and but he does it using the golden rule. But now, look what he has following this. He says, finally, we present a third proof of second De Morgan's law, which is one due to Andres Aguirre, a student at Pepperdine, September 1993. And this is the proof, the way we learned, the way I showed you how to do it.
Pulling a rabbit, though?
Well, yeah, but look how short it is. It is pulling a rabbit out of a hat, but check out how short it is.
You complain because I pull a rabbit.
No. I just made a comment. I wasn't complaining. But anyway, the thing is, this is a really short proof. And what's interesting, there's an interesting story about this, because when his book first came out, when his book first came out, I used his manuscript before the book was published even. And I was teaching all this stuff to our students, to your colleagues from years ago. And I showed, when we were doing the homeworks, and learning how to prove 3.47b, I showed them how, well, this is how you prove 3.47b. And so on an exam, I asked to prove De Morgan B on an exam. And this student, Andres Aguirre, he came up with this just on the exam. And so I was grading the exams, and I thought, whoa, this can't be right. This is only like 3 or 4 steps long. And I looked at it and said, well, sure enough, this is a great improvement of the proof. So I emailed Professor Grease, and he said, whoa, that's a great improvement. And so he included it in his solutions manual and cited the student, Andres, who came up with this for the first time during an exam. So take that as inspiration. Maybe sometime I'll ask you to prove something, and you'll come up with a great short proof, a better proof than what anyone else has thought of before. So see, there's room for improvement.
So when we're doing these proofs, we have to take precedence into account?
Oh, yeah.
I had some trouble with that.
Yeah, absolutely.
Okay.
Yeah, that was an incorrect. The question was, do you have to take precedence into account? So the answer is yes. And the precedence, you remember, all comes. Is here. Here's the table of precedence, but you will have this table. You, of course, on the front. It's the very first thing on your thing, so you can always refer to that. Fortunately, you don't have to memorize this, any of this, but you do have to be able to use it to prove. Okay? All right, so I think what we can do now is we've got an extra, a review session scheduled outside of the regular hour. And I think what we can do now is we have the test on Thursday. Let's just start reviewing, okay? So, where did we start? Okay. Josh, what's the first part of the definition of an expression?
Variable or constant.
Okay, a variable or constant is an expression. What's the second part?
If E is an expression, then parentheses.
If E is an expression, then parentheses E is an expression. What's the third part?
With a binary or unary prefix.
Okay, if circle is a unary prefix operator,
Yeah.
and what?
And
And E
is an expression.
is an expression,
Circle E is also.
then circle E is also an expression, and
Star
Ben?
is a binary infix operator.
star is binary infix.
E and F are expressions.
E and F are expressions. E star F is an expression. Cale, do you remember what's the definition of state? Okay. Do you remember what the definition of state is, Josh?
List of variables and their values.
That's a list of variables and their values. Remember that? Okay, so a list of variables and their values.
Find that.
What's that?
Well, we have to know that.
Well, I mean, this is the kind of stuff that I could ask you on the first question of the test, multiple part,
Shenanigans.
yeah. So you need to know definitions, okay. Then we did lots of examples with textual substitution, but gee, I mean, you do textual substitution now all the time, right? So, and remove unnecessary. I mean, I'm obviously not going to say do one of those questions from chapter 1, do this textual substitution, because you do it all the time now, right? Okay, what's inference rule? What's the shape of an inference rule?
You have the bar.
You have the bar.
And you put, is it the state on top?
Yeah,
But you assume it's valid.
yeah. What you put on the top is an expression that you assume is valid, and then below the bar is what necessarily follows. Okay. So you assume what's on the top. You assume that that's true in all states, and if that's true in all states, then what follows is valid. Okay, so we know the meaning of an inference rule. All right, so here we go. You've done this a bazillion times. Mason, what do you think what is the first characteristic of equality?
First characteristic.
Yeah, there's 4 characteristics of equality. Remember what the 4 characteristics are? RSTL. So what's the R?
Not reflection, but
Yeah, that's right. Reflexive. Yeah, R is reflexive. And what does reflexive mean?
means like that, like E equals E.
Yeah, only we're talking equality. So it was RSTL, and R was reflexive. And what does that mean?
Like, I don't know.
Okay, Ben, what is reflexive? You actually said it. What is reflexive?
Does that mean that is it that's
E equals E.
that it equals itself?
Yeah. Reflexive is X equals X. Okay. And what is the S? Cale, remember what the S is?
Symmetry.
Good. Symmetry.
It's P equals Q equals Q equals P.
Yes. So this would be X equals Y, just using X equals Y equals X. And what was T?
Transitivity.
Transitive. Remember transitive? Transitive was in the form of an inference rule. So what was a transitivity inference rule?
X equals Y, comma, Y equals Z, line
It follows that.
follows that X equals Z.
Good. And L, oh, you got the hard one. L,
Leibniz. And it's also an inference rule.
it's also an inference rule. This is a harder inference rule. Do you remember?
E equals F, then
Yes, if,
E with X replaced by Y equals F with X replaced by Y.
yeah, if E equals F, then, what'd you say?
E with X replaced by Y.
No, because it's another, actually here, let's use X and Y here.
Sure.
If X equals Y, this is substituting equals for equals. So we're going to substitute something with X is equal to something with Y. Remember how that worked?
E with X.
An expression with,
R
let's just, something with Z
replaced by X
replaced by X,
equals the same expression with Z replaced by Y.
yes, is the same expression with Z replaced by Y. Okay, and this is substituting equals for equals. Good. All right, and remember we had some exercises in chapter 1 where we said, well, what if, remember we had some of those? I had you do some exercises where, you know, we had an expression here and we had this and you had to fill in this, or we had one or the other and you had to fill the other. Well, I mean, you should maybe review it. Okay. And this one is substituting equals for equals. Substitute
My
equals.
rule is true too.
I'm sorry, say that again.
It's the Kyle rule.
I didn't get that, but
It's not valid.
Totally is.
and then we talked a little bit about functions. Yeah, we used that dot thing, the dot notation. Remember how that worked?
Yeah.
The dot inside the parentheses.
Yeah, the dot instead of the parentheses. Okay, and I think that's about it. Oh no, we had another really important concept in chapter 1.
This was all chapter 1.
All this is chapter 1.
We only ever learned anything in chapter 1. Alright.
Okay, so let's see who is next.
The Hoare triple.
Remember it was P, S, Q, and let's identify these. P is called the what, Mason? That's the precondition. S is the what? Program statement. And Q is the what? Kale? Postcondition. And what? Yeah, and the question is, what is the interpretation of the Hoare triple? That's
If the precondition is assumed to be true.
if the precondition is,
Statement.
wait, hold on. If the precondition is true, okay, and then and X executes, it will do what?
P will terminate.
No. That's not P will terminate. S is the statement.
Whatever.
Okay, wait a minute, wait.
P is true.
If P is true
And the S is the statement.
and S, the statement executes, it will do what?
Terminate.
It will terminate and what?
Q is guaranteed to be true.
And Q is guaranteed to be true. That's the interpretation of the Hoare triple.
Okay.
So these are the kinds of questions that I would ask on, the first question on the exam. Lots of short answer questions. Okay. And now, what about the definition of the assignment statement? Remember that?
The definition of assignment statement.
Yeah. Do you remember what the definition of an assignment statement was?
No.
You don't remember that? Remember the assignment statement uses the same symbol as textual substitution,
Just gets.
Gets.
but it's gets instead of is replaced by.
What's the difference?
Well, an assignment statement is used in a programming statement.
So no difference.
Well, yeah, it is, because whereas the replacement is used in a textual substitution. Well, no, that's good. All right, so now, do you remember what it was? If we have the assignment statement X gets E, and we have the post condition R, how did we calculate the precondition?
With X gets E.
Only this time we say it's R with X replaced by E. Yeah, so this
Big deal.
is R with X replaced by E.
He's right, it's really not.
Yeah? And we did some examples. So here's another short answer question for the first problem on the exam would be, I'd give you assignment statement and a post condition. You have to figure out what the preconditions. But that's just like simple textual substitution, right?
Yeah. Anyone can do that.
All right. And then we had examples of multiple assignments. Do you remember? Do you remember how to do these? Well, actually, I might ask this. These were kind of tricky. Do you remember how to do this? Here, do you remember how to do this kind of problem? Suppose we have, I don't know, let's say X plus Y, and we have X comma Y gets Y comma X.
Flip it.
Yeah, so this equals, by textual substitution, and remove it, and
Rub it apart.
remove unnecessary parentheses. So what would that be?
Y plus X.
Y plus X. But remember how about this? How about X plus Y, and this time we do X replaced by Y, Y replaced by X.
X plus X.
These two.
So
And rub twice.
yes, so you do textual substitution and remove unnecessary parentheses. Only this time you don't do the textual substitution of this one into the textual substitution. You have to do this first, right?
Right.
Yeah,
So that would be, yeah, so this would be
Plus X.
Y,
X plus X.
X replaced by X. This would be Y plus Y with Y replaced by X. And then this would be, like you said, X plus X, which is not the same as this. Which goes to show you, which shows you how this happens simultaneously, right? It shows you that this is simultaneous, whereas this is not. Remember that? Remember how that works? So we're going to be using that later on when we actually apply all of this stuff to programming.
Yeah. Like, can we use that kind of stuff in a proof? Like the double replacement?
We do that all the time. Whenever you say with PQ replace not QP, or when you say, if you say PQ replace not P not Q.
Do the non-simultaneous.
Oh,
Add to it. Or is that crossing the line?
oh, I see. Like, well, let me think about that.
You could do some really weird stuff.
Yeah.
Oh, that's a good question. Could you?
That would be-
Whoa, because
Good, but it's kind of random.
It could be handy.
Wouldn't that just
I
be
think
the
it's
same?
actually, I think you can. I don't see why you can't, because
you can.
of course you can, because I guess you could, because you know that if this is true, because you know that if some expression is true in all states, it's true with this. Replace that by this.
Right.
Yeah. So the answer is yes, you could.
That might come in handy
Well, I've never seen it done.
Isn't it just like doing
I'm
the
gonna
same
invent a
thing
phrase.
twice?
It'll be one of those proofs you can do it in one step with that, and then your name will go down in history.
Your name will go down in history.
Probably not where I want my name in history, but.
You don't get to put your name in history twice.
Okay.
I don't make the rules.
The next thing we did was truth tables. You guys know the truth tables for all the operators?
Let's not do truth tables, please. They're so redundant and easy. It's not worth our time.
Yeah, in fact, remember that we started with truth tables, and then when we went to the deductive system, we are abandoning truth tables.
What is the truth table for Rhino?
For Rhino.
Yeah, that's right.
What is the truth table for Rhino? I don't know the Rhino operation. What's the Rhino operation? Operator. So we have not, so P, Q, not P, not Q. We have equals. What's equals? If true, 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 false, false, true, false, false. What's the one for equals?
True, false, false, true.
Correct. Got it?
Yeah.
What about equivalence?
True, false, false, true.
True, false, false, true. What's the difference between equals and equivalence? Equals, whoa, whoa, whoa. The truth tables are the same.
Whoa, whoa.
Associative, is that?
Equivalence is not transitive.
No.
Which one is for numbers? Which one is for both numbers and works for both numbers and booleans?
Equal.
Ah,
Equals.
equals.
Equivalence always Boolean.
And it's commutative, right? Is that the word?
They are both symmetric, which means commutative.
But equivalence
What's
is
this?
not transitive and equals is.
What's the other?
I would not say that.
What's
Equivalence is associative.
Because if P
Equivalence, yeah, Ben was right. Equivalence is associative,
Okay.
Yeah.
but what is in contrast, what is equals?
This
Starts with a C.
Conjunctive?
Conjunctive.
Wow.
That's the important thing. Equals is.
And this actually, some of you guys made some mistakes. I've seen on some of the homeworks that I gave back. Actually, here, let's take a look at. Look, let's take a look at the golden rule. In fact, here's the golden rule. Here's the golden rule. The golden rule says P and Q equivals P equivals Q equivals P or Q. Now, if this it has an associative meaning. That means that you can put the parentheses around here, or around here, or around here, or around here. But it is not conjunctive. Some people use the golden rule, but they assumed that equivalence was conjunctive. Like some people said, oh, well, what this says is that P and Q equivals P. They said this equals Q.
Wrong.
But that's incorrect.
Right.
You see, if it were equals, if this were x equals y equals z equals w, then it would be true that x equals z. Are you with me?
Yeah.
By transitivity, but because x equals y, because this would mean x equals y and y equals z,
Right.
and therefore it would be true that x equals z. Or it also would be true that x equals y. But you know, this doesn't say that P and Q equivals P.
Doesn't that mean that equivalence isn't transitive and equals is?
No, hold on. That's a separate issue. Yeah, actually, we're mixing two things here. Look, equivales. Check it out. Because equivales is, look, 3.82. Equivales is transitive. If P equivales Q and Q equivales R, that does imply that P equivales R. But the thing of it is that, but the thing you have to be careful of is that P equivales Q equivales R is not the same thing as P equivales Q and Q equivales R.
Oh, okay.
Do you see what I mean? It's not, yeah, this is subtle. It sounds like you're getting it though. Are you with me here?
Yeah, for sure.
See, I mean, because if you do have this, it is true that P equivals R. I mean, it does imply that. It does imply that P equivals, but this does not mean this.
Right.
That's the point. Yeah, oh, because of the truth tables that they're transitive.
Well, because like for example, P equivals Q equivals R. So like if you had the parentheses around Q equivals R, you
Mm-hmm.
have like a certain truth table, and P would have to equal that, and then you'd have to get the true or false from that.
Sure.
It'd be different.
Yes.
Yeah. Okay. Is everybody good? Actually, there is something that I should mention here probably that I don't think I mentioned when we were going through this the first time in class. If you have a string of, here, if you have a string of equivals like P equivals Q equivals R equivals S equivals T. My question is, when will this be true? Under what conditions will this whole thing be true?
4 falses and a true.
Four falses and a true.
Or 2 falses and 3 trues.
So what's the or
Even
Wait.
number of falses.
Is T true or T a variable?
T is a variable.
Is that right? Even number of falses?
Yeah, if you have a string, well, let me see. It depends on if there's an even number or an odd number.
Exactly. Yeah.
Yeah, so what's the rule? P equivals Q equivals R equivals S. So what's the rule? Can we formulate a general rule?
No.
Maybe, no,
Q and equals R equals S.
say it again?
Like,
Well,
if you separated it by parentheses and they're true.
I think there's a general rule that has an even number of something or an odd number of. What's the rule?
Even
When
number of trues. Falses.
if you have an even number of falses, it will always be true.
Yep.
So what is Q and R?
I think that's right.
That statement is valid.
And even if you have an even number of falses, the string of equivals will always be true. Is that right?
Yep. Yep.
Does everybody
That statement
see
is
where we're getting? An even number of
Yeah.
falses makes the expression true. Yeah. And I think that's something that I was going to point out that I never did point out when we were going over this the first time in class. Are you with me?
Yep.
And this has to do with the associative, You can associative and you can symmetric, because anytime you have an even pair of falses, you can use symmetry to get the false equivals false, but the false equivals false we know is true.
You don't even have to do that though,
Yeah.
because you can take P equals Q equals, or you can just true equals false.
True equivals anything, you can get rid of the true equivals.
Well, there's
Or
that,
you
but
can
you
just
can
say
true
true
equals
equals
false,
false.
that's false, equivals, true equals false, which is also false, then you have false equivals false, which is true.
That's right.
So,
You knew.
Lots of different ways more than one way to skin a cat. Okay, so we did the truth tables.
but we never want to skin a cat.
Well, that's what my father-in-law always used to say. All right, and so we just had a good discussion about the conjunctive meaning versus the associative meaning, the conjunctive meaning for equals compared to the associative meaning for equivals. Oh, the other thing that we did, do you remember this? The other thing we did was the duals. Remember what the dual is?
No. Okay.
Okay.
I don't remember.
What is the dual? Remember what the dual of an expression is?
It's like yeah, it's
You do, what's the,
not
what was the rule for having,
It's like all the ands become ors, but.
yeah, so, yeah, let's see if we can remember what the dual
I
is.
got them all wrong.
Dual.
I mean, all the equivalents mean not equivalent.
Remember what the recipe is? The recipe for dual? So what was the first? I think it was 1, 2, 3, 4. There were five things.
Not goes to or, and or goes to not.
No. No. What were the? I think there were 5 parts to the recipe. Remember what they are? You interchange in the recipe. You interchange. There's 5 interchanges that you make to
All
turn.
true to false.
Okay, so true. You swap true and false. So everywhere there's a true.
We did it when we were talking about definitions.
True,
Setting out.
false.
Same day we defined valid.
It is, yeah. Oh, well, some more definitions we'll have to go through. Okay, but let's finish out the dual. So wherever there's true, you make it false. False, you make it true. So that you flip the true and the false. What else do you flip?
And in order.
And and or. So and you flip with or. And what else do you flip?
Equivalence with not equivalence.
Equivales. You flip that with not equivales.
Implies and does not follow from.
Yes, implies, you flip with does not follow from. And follows from, you flip with
We did write it down.
does not implies. Son of a gun. All right. Now, definition of valid,
Satisfies every state.
true in all states. Valid is true in all states, right?
P equals valid not of the dual of P.
What's the other one? Tautology.
Actually, what is a tautology?
I don't remember.
I'm gonna have to define that.
Yeah, these are all valid questions for the.
Tautology is valid.
Yeah, that's a synonym for valid. Tautology and valid mean the same thing. Remember that? So every one of these theorems is a what? Is a tautology. Every one of these theorems is valid.
Tautology is the noun form of the adjective valid.
Yes, a valid expression, and then a tautology. Oh, very good. Little parts of speech there. Adjectives and nouns. Okay, and then we had what's the definition of a metatheorem?
Theorem of theorem.
It's a theorem about a theorem. And we had this, what about satisfied? What? It's satisfied in a certain state if it is what?
Valid.
No. Satisfied does not mean the same thing as valid.
True.
If it's true. An expression is satisfied in a state if it is true in that state.
Satisfiable, there is a state in which it could be true.
Exactly. Satisfiable,
And it's valid.
And then valid.
and then it's valid if it's true in all states, which means it would be a tautology. So does everybody understand the difference between satisfied, satisfiable, and valid and tautology?
So there are expressions that are not satisfiable.
Correct. You want me to give you one?
Sure.
P and not P.
Boom.
That doesn't make any sense.
Well, actually, we have a theorem that says P and not P does what?
Equivalence false.
Equivalence false. We actually have a theorem.
That's true.
Yeah. Now this is a tautology. But you said there's one that's not true in any state. This part of it is not.
P or not P is the excluded.
Yeah, P or not P is the excluded middle. This one is true in all states. This one is a tautology. This one isn't. Not only is this one not a tautology, but then we have another one. How about this? How about P or Q? Is this a tautology?
No.
Is it satisfied in the state P false, Q false?
No.
Is it satisfiable?
Yes.
Yeah.
Okay.
There you go.
In fact,
Yes.
something that's not satisfiable is the not of any of our theorems are
That's true. You could take the negation of any one of those, and that would be
not satisfiable.
not satisfiable.
Really?
Well, sure, because if those are true in all states, if you not it, it's false in all states, and so therefore it's not satisfiable.
But could you not it and set it equivalence to false, and then it would be true again?
You're right.
You could.
Yeah, you could, and in fact, you could say not each one of these equivalents false, and you'd have another whole set of.
And you could quadruple negate all of them.
And from before, you could say equivalence false, equivalence false. You could tack on an equivalence false to the end of each one of them.
Yeah.
You could have an infinite number of
Double negation and
Double-
equivalence.
Now you see why I said that there's an infinite way to prove every theorem. Okay, and what did we say about, okay, so that's interesting about the dual, but what did we say about the validity? What was that meta theorem that with duality?
Valid of P.
Yeah, we said that if,
Valid.
okay, yeah, we said valid
Parentheses.
P equivalence
Valid. Valid. Parentheses. Not. P sub D.
not the dual.
Yeah.
So P is valid, and it means that
I think
not
I-
the dual of P
It's
is
another one
also
too.
valid.
That's right.
I remember we had a big discussion about this. I remember this is, as I recall, we had a big discussion about
Well, I
this.
just forgot it. Yeah,
Well, you should go review it in the,
On the tape.
yeah, on the recording.
Or it's just in my notes.
Well, yeah. But, okay, so here, let's do, maybe we can do
a
an,
short example.
let's do a short example.
That's just
Let's,
taking the not, okay.
P implies P or Q.
yeah, P implies P or Q. This is valid, right? Because it's one of our P implies P, that's weakening. This is weakening, right? So because this is valid, what else do we know is valid? We know that, well, first of all, let's do the dual. The dual would be what? P does what? Does not follow from
P and Q.
P and Q. And then,
So that's false.
so,
Not a two.
so we know that this is also valid.
Yeah. So that
Because
follows-
the dual-
the dual of a theorem is
Oh, false.
not satisfiable.
Yeah. The dual of a theorem is not satisfiable,
Yep.
and then if you negate it, it's valid.
Well, this says that this is valid if and only if this is valid. Actually, we can manipulate, watch this, check this out. We can manipulate this a little bit. What's the same thing as not, P does not follow from? Because this does not follow from is the same as what? This does not follow from is the same as what?
P,
So this is not P follows from P
Yeah.
and Q. Are you with me? But what's this the same thing as, using double negation?
proving it right now.
This is P follows from P and Q. Are you with me?
Yeah.
But this just happens to be what?
Part of the
No. We started, this one was, which one was this? This one was weakening the consequent. What is this? This is strengthening the antecedent.
so they're opposites.
Well, what I'm saying is that this is valid, and this is an illustration that because this is valid, the negation of the dual is also valid.
So could we use the duals to prove here?
Yeah, no, not. I want you to prove them directly. Okay, so that's illegal.
There's plenty other proof.
There's plenty.
We also proved
Is
a
that a
previous
good
theorem
statement?
to a later theorem too, which is not allowed.
Is that a good statement?
Right,
The
right.
The dual of a theorem is not satisfiable.
Oh, that's a good question. Is the
Think about it.
dual?
It has to be true if the negation of it is always.
Yeah, you're right. If the negation of it, yeah, you're right. It is. Say that again. The dual
The
of a
dual
theorem
of a theorem
is not
The dual
satisfiable.
of a valid statement is unsatisfiable.
That's correct. The dual. That's a nice connection. And then there was one other one.
I'll get my name in the book for that.
You want to get your name in the book?
That'd be awesome. You can-
Okay. And what else did we say? What was the other one? Valid.
Valid P equals Q.
If P equivalence Q is valid, then
Equivalence,
that's-
valid. P sub B equivalence Q sub B.
only this time there's no negation.
Because they're,
It's like false equals false,
they're
which is
both unsatisfiable, which.
No, that, it's not equivalence.
What?
no, that's right.
No, this is right.
Oh.
Because think about it.
There
You
is
have
false equivalence.
two
false.
not satisfiable things are always true.
Well, but the thing that's valid here is the equivalence. I mean, is that P equivalence Q.
Yeah.
See, this whole thing has to be valid. So it's something of the form equal. Let's do an example with something of the form equivalence. Let's go up.
Wait, so does dueling, like, reverse?
Golden rule.
Does dual, like, if you dual something, does it change it from true to false? From false to true?
Yes.
Well, hold on.
Dueling something is all the truths go to false.
Well, but if you can take the dual of an expression that's not valid, and so the dual is not the negation. That's a common mistake, by the way. Are you with me? You can take the dual of an expression that's not valid. It's, by definition, you can take the dual of any Boolean expression.
Right.
But if you take the dual of an expression, it is not the same thing as taking its negation.
Alright. But if you take the dual of something that's valid, it's
Well, if you take
the
the...
same as negating it. Yeah, if it's valid, it's the same as
Um,
Rule of a valid expression.
If you take the dual of a valid
It
expression,
will always be false. If you negate a valid expression, it's always false.
Yeah, that's true.
all right. With that, we'll see you all at the review session and then at the exam on Thursday. And we won't video either one of those. All right? So see you later.